gravelly thing to talk about. I'm trying to think about the way that I want to structure this. I mean, eventually we are going to have to talk about Kepler's first, second, and third law because a lot of gravitational energy comes into play here. Because if you're thinking about circular motion, one of the best places for these things to occur is no, this doesn't all have to do with space. There are cases of circular motion where space isn't really a concern. If you just take an object and you just throw it around in a circle like this is actually a good example of circular motion. This does not involve space. Okay, so there are some cases where we actually discuss circular motion, but that circular motion isn't necessarily regarded to planets moving around back and forth to each other. Okay. Yeah, we will actually talk about escape speed. So this is going to be like half on Earth and then like half off of Earth. So we got to go through the basics first. Okay. Your argument was it's all about space. It's half about space. We're going to go halfsies on this one. Definitely halfsies. But we got to go through the basics first. Okay. Now, whenever we talk about circular, you don't even know how to calculate it because you're not ready for it yet. There they go. More stuff going. It's happening. Circular motion deals with stuff that goes around in a circle. Okay, so oh lordy, tons of stuff. They're just going. They're just going today. The announcements are going. All right. Whew. See if we can get settled in. If you got something that moves around in a circle, and we're going to assume one thing. We're going to assume that whenever we have things that go around in a circle, we're going to assume that it's something called uniform circular motion. And what that means is that means that whenever this thing is going around in a circle, that there is actually no change in the magnitude of the acceleration. Okay, so as you go around, we're going to assume that we're going around at a constant speed. So if we're going around, let's say like 20 meters per second on this side of the circle, whenever you find yourself at any other part of the circle, you're still going the exact same speed as whenever you started. Okay, but that does not mean that there's no acceleration happening. Okay, so we have to think back on the definition of what a vector is and how a vector actually does its stuff. So acceleration has a magnitude and it has a direction. So if you have something that's moving and you try to change its direction to go from this direction to this direction, in the process of moving that, you have actually changed the direction of it. So there had to have been an acceleration that occurred, even if it was moving at a constant speed. So even if that speed was 100% constant, the simple fact that you changed direction means that you had to have had some kind of acceleration happening there in the first place. Okay? So is the speed changing? No. Is there acceleration? Yes. Okay, so that's really what we kind of have to think of here. So there is no change in speed, okay, but there is change in direction, okay, change in direction. And that is where our force for circular motion comes into play. We've been talking about using the line of action all the time. The The line of action is a circle. Yeah, the line of action goes in the circle completely all the way around. Okay, so and now whenever we're thinking about the line of action, our line of action goes through the path of the circle itself. Okay, and probably don't need to put arrowheads there because that normally implies vectors. So I'm going to try that again. Our line of action is along the path of the circle. Okay, and that's how we kind of need to think about this as we continue to move through the chapter in and of itself. Okay? Um, the acceleration for an object in circular motion, the acceleration always points inward. Okay? And that inward acceleration is called a centripetal acceleration. Centripetal. Okay. In America, we call it centripetal. If you're from across the pond, you call it centripetal. It's probably actually better to pronounce it centripetal because then people don't get it confused for the other kind of force that makes me cringe a little bit, which is called centrifugal force. This is what they call a fictitious force. So there is a difference between centripetal and centrifugal. Okay, and we'll talk about why we don't necessarily use this word in physics later. And it's going to kind of depend on how we actually start thinking about rotational motion. But we're going to mainly focus right now on centripetal force and centripetal acceleration. And then later on, once we get to the spot where we know enough to be dangerous, I'll show you guys why we don't use centrifugal. Okay. So centripetal would be a center-seeking force. It always wants to go inside the circle. The centrifugal force would be the opposite. It would be a force that goes outside of the circle. Okay, so there is a Newton's third law that kind of goes along with this, and I'll show you guys where centrifugal force comes into play. But right now, we just are worried about the centripetal force, the center-seeking inward force, because that's what's going to keep you in the circle. Okay, that's what's going to keep you in the circle. It's exactly like a string. Okay. Um, and I think another thing to add to this, and probably like it's one of the most important things that I can say, so it's important to go ahead and say this at the very beginning, is that centripetal force and centripetal acceleration is like a flavor of forces. It is not a force by itself. Okay. So like you don't say like if you have ice cream has several different flavors that go along with it. Okay. If you have a force, forces can have different flavors that go along with it. Okay. Like linear force is forces that go in a straight line. Centripetal forces are forces that go in a circle. So whenever I say that a force is a centripetal force, that means only that it's the flavor of the force that goes in a circle. It is not a force by itself. Okay. Because like if I were to just like say a flavor of ice cream just randomly, you would have to assume that I'm talking about ice cream, right? Because immediately like chocolate comes out. Okay, but like if you said just like randomly chocolate, you would have to make the assumption that you're actually talking about ice cream, right? Because this is a flavor. In the same way, if you just said centripetal, you're going to have to assume that you're talking about forces, okay? And what happens, I would say at least half of the time with like even like even after going through a lesson on circular motion, people will think that centripetal forces are a force by themselves. Okay, actual forces can be centripetal. They can act in a centripetal manner, or they can act in a linear manner. Okay, centripetal cannot be a force by itself, right? It is not some magic force that exists just completely by itself. So, like in the case where you're, twisting, or here, I'll just like make a really, this guy's got a third arm. There we go. It's really long. If you're like twirling something around your head like this, okay, the centripetal force that points inward is tension. So tension is centripetal. Okay. In the case of going on a roller coaster and you do a loop-de-loo, and it goes like this, whoop, all the way around. When you're on the loop itself, there's a force that keeps you in the circle, and that's the normal force. Okay, the normal force is what keeps you in the circle. So in this case, the normal force is the centripetal force. Okay, um, and then if you're talking about like when we go later, gravity, well, like planets and moons will go around an object. The force that actually keeps it in the orbit itself is gravity. Gravity is the centripetal force. So all of these forces, by definition, are centripetal because of the motion that's occurring between them. It is not a force by itself. Okay. Go ahead. Yeah. Yep. Okay. So like when you do a flip, if you do a tumble or a flip or anything like that where you're actually going in a circle, you exert a force on yourself, right? Yeah. So like if you're doing a flip and you're and you're going in a circle like this, so you're already in circular motion, correct? Once you leave the ground itself, you no longer have any push on your body. Okay, so once you leave the ground from this position, there is no more force acting on you. So all of the force that you use to go in a circle has been done at the very beginning. And at that point, an object in motion stays in motion. So whenever you push forward, you take your body and you twist it around to where you actually land on your feet again. Okay? So it's not really a circular motion problem for a flip, it's more of an inertia problem. Because once you push off, you're going. And so by Newton's first law, an object in motion stays in motion. Your objective is to land on your feet, okay, and not on your head. That's yeah, it's not fun doing it the other way around. So your objective is to try to make sure that you leave with enough force that you can actually rotate yourself around, but since there's nothing actually keeping you in the circle, your body is what's doing the rotating, not going in a circle. Okay, so I guess it's probably another thing to talk about. There's the word. Oh crap! I got to think about this. There's rotation and there's revolution. Okay, or revolve. We'll use the word revolve. Okay. And there is a very small difference between the words rotate and revolve. We're going to be focusing on the revolve. We're not going to be focusing on the rotate yet. Okay, so in if we want to get into more detail on how cheerleaders do what they do, that's going to get more into the rotation part and not the revolve part. Rotation is an object that spins. Okay? Revolving is going around a center point. So, correct. The Earth rotates and the Earth revolves. Okay, so like rotation would be like taking a top and spinning that top, and it spins around itself about the axis of symmetry. Okay, revolving would be like the case of like something moving around in a circle around a center point of an object, which would be like, I don't know, like right there. Kind of looks like an eyeball, but whatever. Okay, so rotation, yeah, rotation, the object is the thing actually doing the spinning, and in revolving, the object doesn't necessarily even have to rotate in order to go through centripetal motion or circular motion. Okay, so that's actually a really a clear distinction we need to make between the two. When we get to the rotation chapter, that's the rotational motion. That's whenever we get to like all of the crazy stuff, and y'all don't normally end up liking that chapter very much, but it's actually not that bad. If you're okay with the kinematic equations and every other part of physics, because we basically just take all of physics and we're like, oh, everything that you've learned, now it rotates, and you're like, ah, yeah, what's up? Go for it. Okay. Um, so I think that's my like a little my little soapbox for rotation, revolve, centripetal, and centrifugal. I think we can kind of move on. Um, there are two main units that we're going to use when we deal with circular motion, and that's going to be the conventional units that we deal with in degrees, and the not so conventional units that we're going to use whenever we talk about radians. So if we're doing stuff in circles, sometimes radians actually show up. Y'all are comfortable with the degrees. Y'all aren't necessarily, unless you've had trig or maybe a little bit of. Sometimes y'all do it in geometry, but not really. Okay, so fair enough. If you got a circle and you wanted to measure, because the angle can actually be important, you want to measure the angle from one spot to another. How many degrees are in a circle? Okay, so we've got 360 degrees in a circle, right? Okay, I'll try to do a better job. There are 300, or I'll try to do a different job. How's that? Because sometimes if you just hear it a different way, sometimes it makes sense. Sometimes you can hear it 5 different times, and then like somebody just says it the right way, and you're like, oh, okay, that actually makes sense. So I'll try. I'll try to see what I can do. We're all okay that there's 360 degrees in a circle, right? Okay, we're all okay that a circle has a radius, right? Yeah? Yeah? Okay, we're all okay that the circle has a radius. So, like, we can just describe the distance from the center of the circle to the end of the circle, and we can call that a radius. Okay? The radius length of a circle is a radian. Okay? So, if I take this radius length right here, let's put it in blue. If I take this radius length right here and I wrap it around the circle a certain extent, and once you run out of space, you just stop. Okay? A radius length of the circle that it's on is a radian. Okay? If I literally take that length and I wrap it around the circle, that is the angle measure of a radian. Okay? And what it comes out to is it comes out to what? What? Huh? Is it okay? Did I lost y'all at radius, didn't I? Radian. Okay. I mean like it's this is crazy talk. Okay, so it's a different measure. We call it a radian like this. Okay, a radian. And here's where it comes from. Okay? Your geometry teachers totally told you what the circumference of a circle was equal to. Close. Times pi times the No, that's not correct. It's not pi r. No, it's not pi r squared. No, 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 no. I will okay. I will accept pi times diameter, or I would also accept 2 pi r. Either one of these are okay. Okay, like so maybe your geometry teacher taught y'all the circumference of a circle, but it's yeah, yeah, uh-huh, uh, uh-huh, uh-huh, uh-huh. It's okay. I see how it is. I'm pulling double time. That's fine. Um, I don't get paid for double time. I just get paid in general. They give me my Snickers bar and I'm good to go. All right. So we know that it's pi times the diameter or 2 pi times the radius. Okay. So that means that, well, what would half of a circumference be? Okay. So if I were to just take half of this circumference, that would be just pi r, right? Would be half of the circle. Okay. So, well, isn't that 180 degrees? Okay. So we're going to come up with this fundamental fact that 180 degrees is pi radians. Okay. Or if you don't like pi, if you don't like that symbol, you can also say that's the same thing as 3.14 radians, which we can just call rad for short. Okay. 3.14 radians. And all that we need to do to switch this over is to just use this conversion factor that 180 degrees is pi radians. Okay, we don't actually like 1 radian. If you were to look at just like what 1 radian is, it comes out to some weird number like 63 degrees or something weird like that. We don't really need to know what 1 radian is. We really just need to know that 180 degrees is equal to pi radians, and I can use that as a conversion factor for things that are actually like rotating around. Um, some common spinny speeds that we're actually going to see is um, spinny speeds. I said spinny speeds. I don't even know what you're doing. I don't know. I don't know. I don't know what you're doing. I don't know what you. I don't know what you're doing. You're hijacking my board. Uh, speed. Spinny speed. Spinny speed. RPM is a thing. Y'all know what RPM stands for? Usually revolutions per minute, okay? Or it can also be rotations per minute. So revolutions divided by minutes, okay? This is distance over time, but the distance is not measured in actual like meters or centimeters. It doesn't have a unit to it. It's just how many rotations or revolutions that occur in revolutions per minute. Okay, torque is measured in Newton meters, so it's a force times a lever arm. Okay, so like yeah, you talk about like foot pound, yeah. So those actually do have units both associated to them, but revolutions does not. Basically, revolutions is counting circumferences. It's how many circumferences that happen per minute. Okay, another one that we're going to see really often is the one that's called radians per second. Okay, revolutions per minute and radians per second. Let's see. I can't think of any other ones that we use like super often. RPM is really common in the manufacturing, engineering, machinery, stuff like that. Cars, we have RPM. You don't have radian per second values. Even in other countries, even in Europe, you're going to measure those in RPMs. You don't measure them in radians per second. Yeah, radians per second is a very scientific or mathematical unit. It doesn't really get used a whole lot outside of that. Most of the other times we just use RPMs. We can easily convert RPMs to radians per second and vice versa. So let me show you all how to do that. It's easy. It's easy. It is. Yeah, we do have to change the seconds and minutes. That's true. Okay, so let's say that we've got something that's spinning at 2,000 RPM. Okay, that's 2,000 revolutions per minute. Okay, 2,000 revolutions per minute. So what I need to do is I need to set up a conversion factor, and I need my stuff to cancel out. So the first thing and the easiest thing to cancel out is the minutes to seconds. So I'll say that okay, 1 minute is the same thing as 60 seconds. So I'll put minutes on top and I'll put seconds on the bottom, so that the minutes end up canceling, and then I've got seconds left on the bottom. Okay. Now, the other one that we're learning about right now is the difference between a revolution and our circumference that's actually going here. You're close. It is two. So one revolution is going to equal 2 pi radians. Okay. So one revolution is 2 pi radians. And then we just have to cancel everything out. The revolutions did cancel unit-wise, so revolutions on top by, revolutions on bottom by. So calculator-wise, it's 2,000 times 2 pi divided by 60. Some of that can be mental mathed away, and you can leave the pi's in there or not. It's up to you. It really just depends on your personal preference. There's a lot of college textbooks that will talk about they'll leave the answers in pi, and sometimes you just run the whole thing out. Obviously, if you're an engineer, you're going to completely disrespect the pi and just like decimal it out to infinity. Yeah, hopefully you should only be as you just want to be as precise as you possibly can. Okay, so calculator wise, what does that come out to be? 209.4? Okay. So then that would be radians per second. Okay, so 2,000 RPM comes out to be about 209.4 radians per second. If you want to do this backwards, if you have the radians per second and you want to go the other way, these conversion factors just get flipped over. So if you've got 60 radians per second, and you don't have to do this work every single time, because it doesn't really change. So we can like cram all this stuff together. It's helpful to see it at the beginning. So like I would say 60 seconds is equal to 1 minute. And then on the other side, 2 pi radians on bottom is equal to 1 revolution. And then you would have your RPM value. Let's check and make sure that everything cancels out. Radians doesn't. Seconds on the bottom. Bye-bye. Minutes, we want that to keep. Radians on bottom, radians on top. So we're left with revolutions per minute. That's good. Okay. So instead of doing a number times 2 pi divided by 60, it's times 60 and divided by 2 pi. And that's pretty much that. I mean, that's it. That is how you change RPMs. Okay? That is how you change RPMs to radians per second and radians per second to RPMs. Okie dokie? He's talking about how engineers just basically they just ignore decimals usually, just right off the bat. They just ignore as much of it as they can. What do you get for the radians per second or revolutions per minute down here? I'm like half engineer and half physics person, so it usually doesn't super bother me if you leave out the decimals. I know there are some people who it would. Yeah, there are some people that totally bother you, and that's okay. There's nothing wrong with that. 600-ish, give or take. Okay, let me just write 600 up there. Is that what you want me to do? Just write 600 up there? I can mental math this, but because 60 divided by 2 is 30. 30 times 60 is 180. It'd be 180 over pi, whatever that is, which turns out to be around about 60. Yeah, it's gonna be close. Yeah, you're gonna tell every one of them. They already don't know the difference between a gear and a sprocket, so I mean, I 57.3. Okay, 57.3 radian. Oh no, sorry, RPM. And you can call it revolutions per minute, or you can just write RPM like this. Either one of those is fine. 57.3 RPM. Okay. That's just a quick. So, like, if you ever see any questions that are in RPMs, you're going to immediately change them over to radians per second. In physics, we don't deal with RPMs. In physics, we deal with radians per second because that silly circumference actually makes a big difference in our calculations. And we need our degrees to be in radians. We don't need our degrees to be in degrees. Okay. So all answers should be in radians and seconds. Radians or seconds. This is the KMS system. Kilograms, meters, and seconds. Okay? Kilograms, meters, and seconds. Now, we are on a weird bell schedule today, so how much time do I have left? Do we know? 15? 13. Oh, daggone. Okay, so we're good to go then. Fair. Let's see what's next then. Next in line. Um, I think we want to talk a little bit about acceleration. Oh, I already did centripetal versus centrifugal. Let's go ahead and let's talk about centripetal acceleration. And yeah, let's do that. We got about 13 minutes. So centripetal acceleration. Okay, so like this is going to be like the driving force for things that stay inside of a circle. And we're probably going to have to go back and spend some more time like practicing how to get these velocities to change in terms of like regular velocities and then like angular velocities. But we'll worry about that a little bit later as practice allows us to do. Centripetal acceleration is the inward force that actually causes the thing to stay in a circle. So if you have an object that is, I'm going to just use like an object that's attached to a string, and this string is just like going in a circle. I'm not being very good at drawing my little box though. And so this is on a flat surface, so I don't have to worry about gravity like at all. Okay, I know it kind of looks like it's like spinning around in the middle of nowhere, but just pretend like this is just on a flat surface and it's just moving around this way. Okay? So if I were to look at this object and I were to say, okay, if this is moving at a constant speed and it's, not really, it's not increasing in the amount of circle that it's moving and it's not decreasing in the radius, what would I draw for my forces here of an object that's actually spinning around horizontally this direction? Okay, so yeah, and I don't necessarily want to call it centripetal, but I do want to put an arrow going this way. In this case, the centripetal force is the tension force, right? Okay. I know and there's a lot of teachers that'll teach us by writing FC for centripetal force, and that actually bothers me a little bit because that brings the assumption that you're assuming that centripetal force is a force, and that kind of trips people up. So I'm going to write tension, and we're going to say that tension is acting as the centripetal force. So you're never going to see me write like FC on a diagram. That won't actually occur. Okay. So, and that's just kind of the way that it is for me anyway. Okay. Are there any other forces acting on this if it's moving at a constant speed? Okay. But yeah, so you're right. You're right. In real life, there would be an applied force that kind of pushes it around that direction. Um, but what if it was on like just a frictionless surface? If you started something in motion and it was tied to a string, would it keep going? Okay. So in real life, you would actually have to keep applying a force to keep it going. So in real life, we would have an applied force going one direction and we would have friction going the other direction. So we could write it like this. We could write an applied force that goes this way, FA. This makes y'all happy. And you could write a friction force that goes this way. And those forces are constantly changing direction. So as we keep going around the circle, the tension will keep pointing in, and the FA and the FF will always be tangent to the circle. Okay? The applied force and the frictional force will always be ending up tangent to that circle if you're applying that force on the box itself. Okay? And that's the easiest situation that we can come up with. In reality, there will probably be like because the force is normally coming from like an arm or a motor or something like that. Okay, so like we would probably have to make it a little bit more complicated. We're assuming that this is like some kind of a rocket pack box that has like a set of rockets on the front that's just like pushing it one direction, and the friction would be slowing it down. But usually there's an applied force that comes from some other angle, and life gets more complicated. I don't want to get that complicated yet. I just want to look at the tension and be like, okay, well, if there is some tension acting on this, I certainly hope not. Okay, so like I know that like right here, the sum of the forces in this case, is it moving? Okay, so it is moving. So the sum of the forces is going to have to be equal to the mass of the system, right? Times the acceleration. Is it accelerating? Correct. So since it is constantly changing direction, the answer is yes, it is accelerating. Okay, so it is accelerating. But I can't write the acceleration because this is where we get a problem, right? Well, right, because the sum of the forces is not equal to zero. So, and it makes this even harder because whenever I think about the acceleration is given as a number, and those numbers are linear values. So, if I try to write an acceleration, it'd be in meters per second squared, but it's not speeding up and it's not slowing down. So, if I try to find the actual linear acceleration of this object, this number is always going to be zero, and we're going to get real confused. So what we've got to do is we've got to change our mindset on the acceleration because it's not a linear acceleration, so we can't use our kinematic equations. They're toast. If we used any kinematic equation on the system, there's no acceleration. It would just be distance over time, right? That's the only one that we can use, right? We can't use VF squared equals VI squared plus 2AD. It doesn't work because there's no acceleration. We can't use VF equals VI plus AT because there's no acceleration. So the only thing that we can use is the The only that one's dead too because we don't have any of the acceleration. We can only use velocity is equal to distance over time. What is the distance of a circle? Okay, so we're only going to be able to use 2 pi r over t because 2 pi r is the circumference of a circle. Okay, now we're starting to get somewhere, but we're not quite there yet because I can't just plug in velocity into this expression and then be done because that's not really going to help us out very much. Okay, so we've got that the velocity is equal to 2 pi times the radius over the time, and we need to kind of substitute that in for the acceleration. Okay, now, do you want me to? You have two options at this point. Do you want me to derive this expression for you, or do you want me to just tell you what the acceleration is? Do you derive it? You want to go the whole way? Okay. You want to go the whole way? Well, okay. If you want to derive it, then we're going to have to learn a little. Yeah, we have 5 minutes. We're going to have to go into a little bit more on angular speed and angular velocity and angular acceleration before I can actually derive it the rest of the way. Okay, so if you want the cheat mode, it is on the formula sheet, I believe, and I'm going to have to double check myself on that one, but I think it's actually on there. But we will derive it tomorrow, and then you don't have to derive it again. You'll just be able to use it forever and ever and ever on. I think it is useful to know what the derivation looks like, but this will be a time for another day. If we've only got 5 minutes left, we're going to cut it here, and I think we're good to go.